We get taught that ancient people were primitive, that they thought the world was flat, that real science only started after the telescope, after Newton, after satellites, and almost every single one of those assumptions is dead wrong. The truth is stranger and more impressive than the myth, because over 2,000 years ago, scholars in Egypt, India, and the Middle East were measuring the size of the planet Earth with tools that fit in one hand, and they were getting dangerously close to the right answer. No GPS, no aircraft, no computers, just shadows, sticks, angles, and minds that refuse to accept the universe as a mystery. This is what we actually got wrong about how ancient civilizations measured the Earth. If you value deep, documented science history like this, subscribe. It is the only way to support this work. And drop a comment right now telling us what city you're watching from. This script is factual and research-backed, drawing from the American Physical Society's published history of geodesy, available at aps.org, and from the peer-reviewed academic journal article Alberuni in the Mathematical Geography by AC. Sparavigna of the Politecnico di Torino, published through HAL Science in 2014, not the kind of sources you find on the first page of Google, but the kind that hold up when you check them. Now back to the story. Let's start at the very beginning of the chain. Around 500 BC, the Greek philosopher Pythagoras looked at the night sky and said the Earth had to be a sphere, not because he had proof, but because he believed the sphere was the most perfect shape in nature. That sounds like poetry, not science. And it was. But it planted a seed. 100 years later, Aristotle actually gave physical evidence. Ships disappear over the horizon hull first. The Earth casts a round shadow on the moon during a lunar eclipse every single time, from every angle. Different star constellations are visible at different latitudes. 3 separate observations, all pointing to a sphere. Aristotle was born in 384 BC and was dead by 322 BC, and in that span he shifted educated Greek thinking from guesswork to geometric fact. But knowing the Earth is round and knowing how big it is are two completely different problems. The first serious attempt to crack that second problem was made by a man named Eratosthenes of Cyrene. He was born around 276 BC in what is now Libya, educated in Athens, and then summoned to Alexandria in Egypt by King Ptolemy III to run the most important library in the ancient world. He worked alongside Archimedes. He corresponded with Apollonius of Perga. He was surrounded by the best minds of his era, and one day, probably sometime around 240 BC, he read something in the library's scrolls that changed everything. The document described a peculiar event at a city called Syene, what is now Aswan in southern Egypt. On the summer solstice, the longest day of the year, at exactly noon, the sun shone directly down into a deep well in Syene, not at an angle, straight down. Objects cast no shadows. The sun was directly overhead. Eratosthenes looked out his window in Alexandria. Same day, same hour, shadows. A vertical stick standing in the ground in Alexandria cast a shadow, which meant the sun was hitting at an angle. He measured that angle, 7.2 degrees, 1/50th of a full circle of 360 degrees. Here's the logic, and it is almost annoyingly simple. If the sun's rays are parallel, which they effectively are given the sun is so far away, and one city has no shadow while another has a shadow of 7.2 degrees, then the surface of the Earth must be curving between them. The arc of that curve is 1/50th of the full circle. So if he knew the distance between Alexandria and Syene, he could multiply by 50 and get the full circumference. He hired a team of bemetists, professional walkers whose job was to count their steps across long distances, to pace out the route between Alexandria and Syene. They came back with 5,000 stadia. Eratosthenes multiplied 5,000 by 50, 250,000 stadia. The debate that has consumed historians of science ever since is, what was his stadium? The Greek stad was not a fixed unit. It changed from city to city, from century to century. The philologist Friedrich Hulch calculated in 1882 that the Egyptian stade Eratosthenes likely used was approximately 157.5 meters. Under that conversion, 250,000 stadia equals about 39,375 kilometers. The actual polar circumference of the Earth is 40,007 kilometers. The actual equatorial circumference is 40,075 kilometers. Eratosthenes was within roughly 1%, maybe less. Think about that. A man in Egypt in 240 BC, with a stick and a team of walkers, measured the size of the entire planet to within a fraction of a percent of what our satellites confirm today. The American Physical Society's published history notes that his method remained the basic approach to measuring the Earth for more than 2,000 years. But here's the thing people almost always skip. Eratosthenes himself knew his measurement had error sources built into it. His 3 key assumptions: that Syene lay exactly on the Tropic of Cancer, that Alexandria lay due north of Syene on the same meridian, and that the sun was so far away its rays hit the Earth in parallel. None of those are exactly true. Aswan is actually about 3 degrees of longitude east of Alexandria, not directly south. Sayeni sits at 24 degrees north latitude, while the Tropic of Cancer is at about 23.4, and the sun's rays are parallel only as an approximation. But the errors, remarkably, partially cancelled each other out, which is part of why the result came so close. The knowledge did not die with him. It traveled. Within a few decades of Eratosthenes completing his calculation, another Greek scholar named Posidonius tried his own version using the star Canopus instead of the sun. He measured the difference in the star's elevation angle from Rhodes and from Alexandria, which lay roughly along the same meridian. But Posidonius had a bad number for the distance between Rhodes and Alexandria. He used a figure far smaller than the actual distance of about 800 kilometers. His answer came out to roughly 18,000 miles for Earth's circumference, nearly 7,000 miles too small. He published it. Scholars read it. And then Claudius Ptolemy, the 2nd century AD astronomer and geographer, whose works dominated Western science for over 1,000 years, included Posidonius' smaller number in his geography treatise. Ptolemy's geography became the reference text, and the wrong number was locked in. The right answer was right there, in Eratosthenes' work. 250,000 stadia, which converted to something very close to 25,000 miles. Ptolemy knew the number existed, but in his Almagest and his geography, he went with Posidonius' smaller Earth. And that decision, made in the 2nd century AD, eventually sent Christopher Columbus across the ocean in 1492, based on a planet that was about 25% smaller than the real one. Columbus did not discover that the Earth was round. Every educated person in Europe already knew that. What Columbus got catastrophically wrong was the size. According to the IEE Spectrum's published history of the voyage, Columbus used figures from the medieval Persian geographer known as Alfraganus, who stated that 1 degree of latitude equaled 56.67 miles. Columbus's first error was assuming Alfraganus was using the Roman mile of 4,856 feet. He was actually using the Arabic mile of 7,091 feet, a unit 33% longer. Columbus compounded this with a second error. He stretched Asia eastward across his maps until Japan nearly touched the Azores. He calculated the distance from the Canary Islands to Japan at about 3,080 nautical miles. The actual distance from Tenerife to Jakarta is 7,313 nautical miles, a 58% margin of error. The World History Encyclopedia notes that Toscanelli's map, which Columbus used, depicted the Earth as roughly 25% smaller than it is and ignored Eratosthenes' measurements entirely, though they had been available in Greek texts for over 17 centuries. Columbus's expedition succeeded only because a continent he had no idea existed was sitting exactly in the path he was traveling. His critics at the Spanish and Portuguese courts were actually right. The planet was too big to sail around with the supplies he was carrying. He was wrong. The Americas saved him. Now step back in time almost 1,000 years from Columbus to a different civilization, a different continent, and a different approach. Around 476 AD, a child was born in Pataliputra in northern India, the city we now call Patna in Bihar. His name was Aryabhata. He was 23 years old in 499 AD when he completed his most important work, the Aryabhatiya, a Sanskrit treatise covering mathematics, astronomy, spherical geometry, and the size of the cosmos. 121 verses, packed with calculations that would not be matched in Europe for nearly 1,000 years. Aryabhata stated clearly, "The Earth rotates on its own axis. Stars do not move. The stars appear to move because we are spinning." He wrote, "Just as a man in a boat moving forward sees stationary objects moving backward, so are the stationary stars seen by people on Earth as moving toward the west." In 499 AD, in India, a 23-year-old mathematician described relative motion. In Europe, scholars were still arguing about whether the heavens physically rotated. On the Earth's circumference, Aryabhata calculated 4,967 yojanas, where 1 yojana equaled 5 miles. That gives 24,835 miles. The Earth's actual circumference at the poles is 24,859 miles. Aryabhata was off by 24 miles, less than 0.1%, written in Sanskrit verse and coded in a mnemonic system, in the 5th century AD out of Pataliputra. The challenge with Aryabhata, as with Eratosthenes, is that accuracy depends on the unit conversions. The yojana is contested. Wikipedia's entry on Earth's circumference notes that one reading of Aryabhata's text gives a diameter equivalent to 14,200 kilometers, too large by 11%. Another reading gives 13,440 kilometers, too large by 5%. Scholars disagree. The range of interpretation spans from impressively accurate to meaningfully off. What is not disputed is the method and the spherical Earth model at its core. Meanwhile, Aryabhata's Aryabhatiya was translated into Arabic around 820 by Al-Khwarizmi. Yes, the mathematician whose name gave us the word algorithm. His translations became curriculum in Baghdad's House of Wisdom. The numbers, the methods, the logic crossed languages and centuries. They landed in the hands of the Abbasid Caliphate, just as Islamic science was hitting its peak. Around 830 AD, the 7th Abbasid Caliph, Al-Mamun, born September 14th, 786, in Baghdad, decided he wanted the most accurate measurement of the earth that had ever been produced. He was already funding the translation of ancient Greek texts into Arabic, paying translators in bags of silver. He had built the first observatory in Baghdad and a second in Damascus. He employed Al-Khwarizmi, Sind ibn Ali, and a rotating constellation of astronomers and geographers at his House of Wisdom. Now he wanted an original, empirical measurement of the planet's circumference. He sent 2 teams of astronomers out into the flat Syrian desert toward the plain of Sinjar. One group walked due north from a fixed point. The other walked due south. They walked until each team had covered exactly 1 degree of Earth's arc, measuring the angle to the stars with precision instruments and counting their paces with care. Then they turned around, walked back toward each other, compared their distances, and averaged the results. The northern team measured 1 degree as 56 2/3 miles in the Arabic unit. The southern team measured 57 miles. The average, when multiplied by 360, yielded a total circumference of approximately 24,500 miles. The actual circumference is 24,901 miles. Al-Mamun's teams were roughly 400 miles off, an error of less than 2%, using no instruments beyond an astrolabe and trained human legs in the Syrian desert in the 9th century. As recorded in Smart History's peer-reviewed arts and history platform, astronomers working for Al-Mamun in the 830s calculated the circumference of the Earth and improved on ancient measurements. Al-Mamun was not satisfied with one measurement. He sent the teams out to the Syrian desert to repeat the experiment and verify. But the most astonishing individual act of geodesy in the ancient world may have been performed not in Egypt, not in India, and not in Syria, but in what is now Pakistan, by a Persian scholar named Abu Rayhan al-Biruni. Al-Biruni was born in 973 AD in Khwarazm, the region near the Aral Sea. He wrote approximately 150 books on mathematics, astronomy, physics, geography, pharmacology, and history. He was fluent in Arabic, Persian, and Sanskrit. He corresponded with Avicenna, the physician and philosopher, in a series of letters that survive to this day. He traveled to India with Mahmud of Ghazni's armies and spent years interviewing Hindu scholars, learning Sanskrit, and documenting Indian science. In 998, at the age of 25, he had already published his first major work on historical chronology. Around the year 1020, Al-Biruni was in the Punjab region of what is now Pakistan, near a place called Nandana, the ruins of which still stand in Pindadan Khan. He wanted to measure the Earth's circumference, but he was alone. He had no partner city to compare shadow angles with. He had no long, flat desert to walk across with 2 teams. What he had was a mountain, an astrolabe, and trigonometry. His method had 2 steps. First, he measured the height of the mountain at Nandana using nothing but 2 elevation angles and a known horizontal distance. He stood at point A, measured the angle to the mountain's peak, walked to point B, a known distance further away, and measured the elevation angle again. 2 triangles, 2 angles, 1 known distance, and trigonometry told him the height of the mountain. This is a calculation students do in high school today. The second step was the stroke of genius. He climbed to the top of the mountain and looked out at the horizon. He knew that because the Earth curves, the horizon is not perfectly level. It dips slightly below true horizontal when viewed from a height. He used his astrolabe to measure the angle of that dip. That angle, which he called the dip angle plus the height of the mountain, plugged into a formula he derived himself from spherical geometry, gave him the radius of the Earth. Al-Biruni's stated result was 12,803,337 cubits. Depending on which cubit length is used in conversion, his radius comes out to between 6,335 and 6,340 kilometers. The actual mean radius of the Earth is 6,371 kilometers. He was within roughly 30 to 40 kilometers, less than 1% off. Published in his Codex Masuticus in 1037. The caveats are real. Scholars at That's Maths, published in June 2021, note that Al-Biruni was not aware of atmospheric refraction, the bending of light near the horizon that affects dip angle measurements. Without accounting for refraction, the method would be expected to overstate the radius by a meaningful margin. The fact that he got a number so close to the real value may reflect partially compensating errors, and some historians are rightfully skeptical of the claimed 1% accuracy. Amelia Carolina Sparavigna, writing in the peer-reviewed publication Philica and hosted through HAL Science, notes that his results sit within the range of plausible accuracy for his tools and methods, but that the qubit conversion uncertainty means the final number cannot be pinned down perfectly. What cannot be disputed is the method itself. Al-Biruni figured out how to measure the planet from a single mountain. No partner city, no walking teams, just geometry and patience. In his Codex Masuticus of 1037, he also made another extraordinary claim. Based on his measurement of the Earth's circumference and his calculation that Afro-Eurasia covered only about 2/5 of the total surface area, there must be another major landmass on the opposite side of the planet, sitting in the vast ocean between Asia and Europe, a landmass with habitable latitudes and therefore inhabited. He published this inference 455 years before Columbus set sail in 1492. Now, here's where everything collapses and gets rebuilt simultaneously. The common myth is that we went from ancient accuracy to medieval ignorance to modern precision. That is not quite right. What actually happened is more complicated and, frankly, more interesting. If you value documented, factual history like this, subscribe. It is how you support the work and help us keep going deeper. And if you haven't commented your city yet, do it right now. Back to the story. The real problem was not a lack of knowledge. It was a transmission failure combined with authority bias. Eratosthenes' correct number was 250,000 stadia, approximately 25,000 miles. Posidonius' incorrect number, endorsed by Ptolemy, was closer to 18,000 miles. Both numbers sat in ancient texts. European scholars in the 15th century had access to Ptolemy's geography, freshly translated into Latin starting in 1406 by the Florentine scholar Jacopo Angeli da Scarperia. They did not automatically also inherit Eratosthenes' original text, which survived only in fragments and summaries. But here's the twist that the textbooks never tell you. Ptolemy's geography itself included explicit warnings. Ptolemy acknowledged that his values were uncertain. He even included a section describing how the stade unit was ambiguous. But when cartographers and explorers got hold of the maps, they took the numbers as gospel. The map became the authority. The caveats got lost in translation, literally. Meanwhile, in the Islamic world, the scholars who had access to all the source texts, including Eratosthenes, Aryabhata, through Al-Khwarizmi's translations, and their own original measurements from Al-Mamun's expedition, were producing correct values for Earth's circumference as early as 830 AD. Al-Farghani, also known as Alfraganus, wrote the Compendium on the Science of Stars in the 9th century. In this text, he gave the Earth's circumference based on Al-Mamun's measurements as approximately 24,500 miles. This text was translated into Latin by John of Seville in the 12th century and by Gherardo da Cremona in the same period. It circulated in Europe. Columbus read Alfraganus. He cited Alfraganus, but he converted the units wrong, Roman miles instead of Arabic miles, and ended up with a number 33% too small. The correct answer was right there on the page he was holding. He misread the footnote and sailed into history. Now here is the piece of the story almost no one tells. In 1474, 18 years before Columbus's first voyage, a Florentine astronomer and cartographer named Paolo dal Pozzo Toscanelli wrote a letter to the King of Portugal outlining a plan to reach Asia by sailing west across the Atlantic. His letter included a map. That map, as analyzed by World History Encyclopedia in October 2024, depicted the Earth as roughly 25% smaller than it actually is, exaggerated the eastward reach of Asia, and explicitly ignored Eratosthenes' measurements, which had been in Greek texts for 1,700 years. Columbus obtained a copy of this letter and map. He used them as his primary reference. He then added his own errors on top of Toscanelli's errors and calculated Japan at roughly 3,080 nautical miles west of the Canary Islands. The real distance to Southeast Asia from that point is over 7,300 nautical miles. His contemporaries knew he was wrong. The committee of experts convened by Queen Isabella of Castile said his numbers were too small. Portuguese navigators said the ocean was too wide. Columbus argued, insisted, and eventually persuaded based not on correct calculation, but on sheer confidence in the logic that even a smaller planet was worth trying. He got lucky. The continent in his path did not appear on any map he had ever seen. And here is the final irony that pulls everything together. When Spanish explorers began crossing the Americas and reaching the Pacific coast in the 16th century, the size of the new landmass made it immediately clear that the Earth was bigger than Ptolemy's number. Within decades of 1492, European cartographers were scrambling to reconcile what explorers were finding with the theoretical frameworks they had. They went back to the ancient texts. They found Eratosthenes. By 1600, the Flemish cartographer Gemma Frisius and his student Gerardus Mercator of the Mercator projection were working with numbers far closer to Eratosthenes' original figure than to Ptolemy's. The correct measurement had always been there. It had been sitting in a library in Alexandria 240 years before the birth of Christ, written in a book called On the Measure of the Earth by a Greek polymath who got it from a shadow in a well and a team of professional walkers. The book itself did not survive. Eratosthenes' original work, the full text of On the Measure of the Earth, is lost. We know his method only through a simplified summary written by Cleomedes, a later Greek author whose own dates are uncertain. possibly 1st or 2nd century AD. The primary source is gone. We are working from a second-hand account of an experiment that was accurate enough to measure the planet. There's one more figure in this chain who never gets sufficient credit. Around 476 AD through 550 AD, a 23-year-old scholar in India, working at the University of Nalanda, the same institution that trained Buddhist monks from across Asia, completed a text that quietly beat most of the Western world to the correct answer by over 900 years. Aryabhata stated the Earth spins. He calculated its circumference within what some sources place at 67 miles of the modern value. He wrote it in 121 Sanskrit verses, and most European scholars had no idea the text existed for centuries. When Al-Khwarizmi translated the Aryabhatiya into Arabic around 820, the knowledge moved west. When Al-Mamun sent his teams into the Syrian desert around 830, they were standing on the shoulders of Aryabhata, whether they knew it or not. When al-Biruni climbed a mountain in Pakistan around 1020, he was extending a chain that ran back through Baghdad, through Nalanda, through Alexandria, to a well in Siene, where the sun hit the water straight down on the longest day of the year in around 240 BC. The Earth is 40,075 kilometers around at the equator, 40,007 kilometers around the poles. Eratosthenes got within a fraction of that with a stick and a shadow. Aryabhata got within 67 miles with Sanskrit verse. Al-Mamun's teams got within 400 miles walking through a desert. Al-Biruni got within perhaps 30 kilometers using a single mountain and a dip angle. None of these men had computers. None had satellites. None had even basic thermometers or clocks in any modern sense. They had geometry and the willingness to look carefully at the world around them. The myth that ancient civilizations did not know the Earth's size is not just wrong. It is backwards. For long stretches of history, the most accurate knowledge was already there. In Alexandrian libraries, in Sanskrit treatises, in Baghdad observatories. The problem was not that the knowledge did not exist. The problem was that the wrong numbers kept getting copied and the right ones got lost, misread, or politically inconvenient. Columbus set sail in 1492 with a planet in his head that was about 25,000 miles too small. Eratosthenes had calculated the correct answer 1,700 years earlier. The answer was on the shelf. Columbus just grabbed the wrong book. In 2020, a team of researchers published a paper on academia.edu titled How the Ancient Egyptians Had Calculated the Earth's Circumference Between 3,750 and 1,500 BC, noting that Eratosthenes may himself have been drawing on much older Egyptian measurement traditions when he chose his observation points at Siene and Alexandria. If that analysis holds, the chain of accurate Earth measurement may stretch back not 2,200 years, but over 4,000. The well at Siene was not just a curiosity. It may have been a deliberate observation instrument used by Egyptian priests to mark the summer solstice for generations before a Greek librarian ever heard of it. The shadow in the well did not prove the Earth was round. The people who used that well already knew. They just had not written it in a way Europe could read. That is the thing about suppressed knowledge. It does not disappear. It waits. Let us go back and stay longer with each of these men, because the details are where the real story lives. Eratosthenes was not just a librarian. He was the chief librarian of the Library of Alexandria, the greatest intellectual institution in the ancient world, holding hundreds of thousands of scrolls at its peak. He was born in Cyrene, in what is now northeastern Libya, studied in Athens under the philosopher Ariston of Chios, and was brought to Alexandria by King Ptolemy III around 245 BC to run the library. He held that position until he died, probably around 194 BC, blind, aging, and reportedly having stopped eating after losing his sight in old age rather than live without the ability to read. A man who measured the world by observation, ending his life because he could no longer observe. His colleagues thought he was a generalist. They called him Beta, the second letter of the Greek alphabet, meaning he was second best at everything rather than the best at one thing. He was second at mathematics because Archimedes was right there, second at astronomy because Hipparchus was coming, second at geography because, well, he was probably first at that. He invented the discipline. He coined the word geography. He created the first world map with a grid of latitude and longitude lines. He calculated the tilt of Earth's axis at 23 degrees, 43 minutes, and 40 seconds. The actual value for his era was 23 degrees, 43 minutes, and 40 seconds. Not approximately, exactly. He got the axial tilt right to the arcsecond. But the Earth's circumference is what he is remembered for, and the measurement that gets rehearsed in textbooks strips away everything that made it brilliant. The shadow and the well are the story, but the deeper story is what the measurement required. First, a conviction that the Earth was spherical, not poetic, not philosophical, but geometrically necessary to explain why shadows behave differently at different latitudes on the same day. Second, a working theory of how light travels, specifically that light from a source as far as the sun hits the Earth in effectively parallel rays. Third, the confidence that a measurement taken at two specific points could represent a universal constant, that the Earth's curvature was consistent all the way around. Fourth, the ability to translate angle measurements into linear distances using the arithmetic of circles. Fifth, a measurement system reliable enough to turn walking steps into geographic distance. He had all five. In 240 BC, the Bemetists, the professional distance walkers, were an actual institution in the Greek world, used for military surveys and commercial mapping. They trained. Their steps were calibrated. The 5,000 stadia they returned was not a guess. It was a measured result from trained professionals walking a known route. The summer solstice was the key. On June 19th, 240 BC, the date calculated from historical records, Eratosthenes stood in Alexandria with a gnomon, a vertical rod, and watched the shadow. The shadow told him 7.2 degrees, 1/50th of a circle. He had his number. The calculation took seconds. The preparation had taken years of reading, thinking, and building a model of the world in his head that was accurate enough to let a shadow tell you the size of a planet. Now Posidonius, born around 135 BC, died around 51 BC. He was a brilliant man, philosopher, historian, geographer, astronomer. He studied at Athens, lived on Rhodes, traveled throughout the Mediterranean and to Spain to study the tides. He used the star Canopus to attempt his own measurement, observing its maximum elevation above the horizon from both Alexandria and Rhodes. Canopus barely clears the horizon from Rhodes, about 5 degrees above it. From Alexandria, it rises higher. The difference in those angles should represent the arc of the Earth between the two cities. His angle difference came out to about 7.5 degrees, or approximately 1/48th of a circle. So far, reasonable. But then the distance between Rhodes and Alexandria. He had a bad number. He used 5,000 stadia. The actual distance is closer to 3,700 stadia. His Earth came out far too small, about 180,000 stadia, translating to something in the range of 18,000 miles, off by nearly 7,000 miles. What makes the Posidonius story genuinely tragic is that it was correctable. Multiple Greek ships made the run between Rhodes and Alexandria. The distance was knowable, but no one, apparently, went back and checked the input. The calculation was trusted once it was published, and Ptolemy trusted it even more because Ptolemy was building an authoritative reference work and needed clean numbers to cite. Ptolemy's geography is a masterpiece and a disaster simultaneously. The masterpiece. Ptolemy provided coordinates for over 8,000 locations around the known world. He described methods for map projection. He explained the difference between measured distance and calculated distance. He was intellectually honest about the limitations of his sources. The disaster. He chose Posidonius's small Earth for his reference figure, and he dramatically overestimated the eastward extension of Asia. His Mediterranean came out 63 degrees of longitude long. The actual measurement is about 42 degrees. And all of this went into maps that European scholars reproduced for over 1,000 years because Ptolemy was Ptolemy. The authority of his name carried more weight than the accuracy of his numbers. When Jacopo Angeli da Scarperia translated Ptolemy's geography into Latin in 1406, it was the first Latin translation of the text in European history. It immediately became a reference. It was printed multiple times in the 1400s. It shaped European geographic thinking for the entire age of discovery. And it had the wrong Earth size baked into every page. Now hold that timeline against what was happening in Baghdad. Al-Mamun became the 7th Abbasid caliph in 813 AD after a brutal civil war with his brother Al-Amin. Al-Amin lost, was beheaded in 813. Al-Mamun inherited the most powerful Islamic empire in the world and immediately turned a significant portion of his resources toward science. He established the House of Wisdom in Baghdad around 830. He paid translators in silver, literally bags of silver, to render Greek, Indian, Persian, and Syrian texts into Arabic. He corresponded with the Byzantine emperor in Constantinople, asking him to send ancient Greek manuscripts for translation. He personally broke into the Great Pyramid of Khufu while on campaign in Egypt, reportedly disappointed to find only an empty sarcophagus and some bones after the centuries of plunder before him. He also built the first Islamic observatory in Baghdad, a round building inside the round city Al-Mansur had constructed in 762 AD, and a second observatory in Damascus, so that data from two locations could be compared. He was not just collecting knowledge, he was generating it. His astronomers established accurate figures for the precession of the equinoxes. They corrected Ptolemy's overestimate of the Mediterranean's longitude span. They produced a new large world map, which has since been lost. And they walked into the Syrian desert in two teams to measure the planet directly. The flat plain near Sinjar in what is now northwestern Iraq was chosen for a specific reason. It was measurably flat. Walking measurements of an arc degree require flat terrain because hills and valleys introduce elevation errors. The teams used theodolite-like instruments to track celestial angles as they walked. One team walked north. One team walked south. Each team walked until the star angles confirmed they had moved exactly 1 degree of latitude. They measured the ground distance covered. The northern team's result, 56 2/3 Arabic miles per degree. The southern team, 57 Arabic miles per degree, average 56 5/6, multiply by 360 degrees, 20,400 miles in Arabic measurement. Converted to modern units using the Arabic mile as approximately 1,973 meters, the circumference comes out to roughly 40,239 kilometers. Actual value, 40,075 kilometers. Within 200 kilometers, about 0.5%. Al-Mamun sent them back to verify. They walked again. In the Syrian desert, the second measurement confirmed the first within acceptable range. He published the result through Al-Farghani's compendium, which spread the number westward through Europe after translation. Back to al-Biruni. He carried the knowledge further and the method further than anyone before him in a single lifetime. At 25, in 998, he published chronological history. At 27, he was already exchanging philosophical letters with Avicenna. He spent years imprisoned and displaced when the Mamunid dynasty of his home region fell to Mahmud of Ghazni in 995. Yes, the same Al-Mamun family name, different rulers, before eventually joining Mahmud's court as something between a captive and a court scholar. He traveled with Mahmud's armies through India 11 times between roughly 1000 and 1030. He learned Sanskrit. He read the Aryabhatiya in the original. At Nandana Fort in the Salt Range of Punjab, ruins that still stand today in Pakistan, identifiable in satellite imagery, al-Biruni conducted his measurement. The fort sits atop a ridge with an unobstructed view of the flat Jhelum River plain below. Ideal geometry for his purpose. He had already calculated the mountain's height using his two-angle method. Then he stood at the peak and looked at the horizon. The dip angle, the angle between true horizontal and the line of sight to the horizon, was small, very small, maybe 0.5 degree, maybe a full degree. An astrolabe in the early 11th century could measure angles to about 0.5 degree accuracy on a good day with a large enough instrument. Al-Biruni apparently had a large astrolabe, possibly purpose-built for this measurement. He measured the dip. He plugged the dip and the height into his formula, the formula he himself derived, which appears in his Codex Masuticus and related texts. The formula is elegant. Earth's radius equals the height of the mountain, times the cosine of the dip angle, divided by 1 minus the cosine of the dip angle. Simple algebra, solved for radius. He recorded his result as 12,803,337 cubits. He converted it to miles, 3,928.77 miles, he said, for the radius. Modern value, 3,958.8 miles, less than 1% off. The caveat that the Thats maths analysis raises is important. Atmospheric refraction bends light near the horizon. When you look at the horizon, you're not actually seeing the true geometric horizon. You are seeing slightly past it because light curves slightly around the Earth's surface in dense lower atmosphere. This makes the horizon appear lower than it geometrically should be, which makes the dip angle appear larger, which makes your calculated Earth radius come out larger. Without knowing about refraction, and al-Biruni did not, the expected error from refraction alone would be on the order of 15% overstatement. Yet his result is only about 1% high. This does not add up perfectly, which is why skeptical historians flag it. The probable explanation is a combination of compensating errors in his height measurement and his dip angle measurement that happened to cancel. It does not make his method less brilliant. It makes the result less certain than it sometimes gets presented. What is certain is the Codex Masuticus itself, completed in 1037 and dedicated to Sultan Masud of the Ghaznavid dynasty. In it, al-Biruni also wrote the Americas prediction. He had measured the Earth. He had mapped Afro-Eurasia's extent. The landmass he could account for covered only about 2/5 of the total surface. The remaining 3/5 was ocean, or land no one had yet described. Logic and mathematics said there had to be more land somewhere in that vast Western Ocean, at habitable latitudes. He wrote it down. In 1037, the Americas were first encountered by a European expedition in 1492. Al-Biruni's prediction preceded that by 455 years, grounded not in mythology or rumor, but in geometric reasoning, from a measurement he conducted on a hillside in Pakistan. And here's the number that closes the loop. The actual circumference of the Earth, measured by the GPS satellite network, confirmed by geodetic stations on every continent, verified to sub-centimeter accuracy, 40,075 kilometers at the equator, 40,007 kilometers through the poles. Eratosthenes, standing in Alexandria with a stick in the ground in 240 BC, approximately 39,375 kilometers by the most accurate conversion of his units. Error, less than 2%, possibly less than 1%. The shadow in the well, the team of walkers. The angle, 7.2 degrees. The math, multiply by 50. The answer, close enough to measure a planet from a library with a stick. He was 45 years old when he published it. The number was right. The world was not ready to keep it.